Okay.
All right, well, it is 4 o'clock, everybody, and people are still trickling into the room right now. So I'll just go ahead and get the boilerplate introduction started and buy them some time to finish connecting. Welcome back, of course, to the SMU Physics Department Speaker Series for Fall 2020. And we're continuing our November series and its theme of New Frontiers in Physics. So in a moment, I'm going to hand things over to Professor Jody Cooley to introduce our speaker, Professor Tongyan Lin. But before we get started, a few reminders, especially for the audience on Zoom. We've got everybody muted by default. If you want to ask a question, just go into the chat window, type the word speak either during the talk or in the Q&A part after the talk, and that'll create a little speaker queue, and we'll get to you in the order we see that appear. We usually try to interrupt the speaker at the end of the next slide, during the next slide change, that kind of thing. You'll only be able to speak when a moderator unmutes you, so I'll try to handle that today for everybody. This event is being recorded, and it's also being simultaneously live streamed on YouTube. That stream is non-interactive, so hello to our viewers on that stream as well. And without further ado, let me welcome Professor Jody Cooley to introduce today's speaker. So Jody, take it away.
Hello, everyone, and welcome to the SMU Physics Department Colloquium. I'm very pleased to be able to introduce Tongyan Lin as today's speaker. She's an assistant professor of physics at the University of California in San Diego. She obtained her PhD from Harvard and was previously a postdoctoral scholar at the Kavli Institute for Cosmological Physics at the University of Chicago and at the University of California in Berkeley. She's a theorist who's studying ways to detect particle interactions of dark matter, including signatures in astrophysical data and underground direct detection experiments. I also want to mention that Tongyan is one of the co-conveners of the Cosmic Frontier Subtopical Working Group 1, which is on particle dark matter. So she is seen as someone in the community that is a real leader. And I know that in my experiment, we're always very interested to hear about her ideas and her thoughts, as many of them are relevant to the Super CDMS program. So Tongyan, thank you again for coming and talking with us today. And I can't wait to hear your talk.
Yeah, thank you so much for the invitation and the kind introduction. So we did check the setup earlier, but I was having a small amount of trouble again. No so worries. I really apologize for that because we just checked it.
Sure. So, no, it's fine.
Yeah, what's happening is if I do play, it says sharing is paused. So do you see any transitions?
No, it's a blank screen, unfortunately. Yeah.
Yeah. Yeah. So
let me see. You are set up as a co-host, so.
So you don't see even anything right now.
Well, now we do. Yeah. So we just don't see it full screen.
Whoops.
Go ahead, Jody.
Oh, sorry. So Tongyan, because I also use Keynote and I've had all kinds of difficulties with Zoom. I found something that works out really good. If you go in Keynote into, let me remind myself what the menu is again. Let me call it my Keynote. Go into the menu that says play and then play show in window. Okay. And then from here, when you share your screen, just share the window that is playing your slideshow.
Okay, let me try that again.
Yeah. Perfect.
Okay, this seems.
Yeah, I see the. Yep, perfect. This looks perfect. I accidentally tripped upon this trick several weeks ago, and it has made my life so much better.
Yeah, thank you. That's very helpful because I already went through like one cycle of how to make Zoom work with Keynote. Okay, so sorry about that. But thank you again for the nice introduction and the opportunity to tell you about some of the work I've been doing. So I work a lot on various ways to detect dark matter from a dark matter theorist perspective. And in this talk, I'll be giving an overview of some of the techniques and approaches for looking for dark matter below the GeV mass scale. How do we detect nuclear recoils from such low mass dark matter? And I'll describe some of the different crystal targets we can use to search for such low mass dark matter. So here's a picture showing a broader motivation for why I want to study this mass range. So these are some of the existing limits for dark matter nuclear recoils. So the traditional approach is to say we're living in a dark matter halo. The dark matter is coming towards us. There's a dark matter wind, and it has pretty high kinetic energy when the dark matter is very heavy. So it can knock a nucleus, and that's like a hard recoil that that can be easily observed if it's energetic enough. And there are many experiments that not only observe this, but have pushed the background so extremely low that they can observe one such event happening in a year with a kilogram of detector material. So that's all of these types of bounds. On the other hand, you see that they're dropping off in sensitivity quite rapidly as we go to the GeV mass scale and below. So these are bounds on the cross section, and you see there's like 10 orders of magnitude between the limits at 10 GeV and 1 GeV. So the question is, how do we explore this pretty big, wide open parameter space for dark matter? And how do we test, there are a lot of interesting theories. I won't have time to get into them, but how do we test lots of interesting theories for dark matter below the GeV mass scale? So let me go over some of the challenges and general approaches to this problem. So the fundamental challenge for why the sensitivity drops so much is that the kinematics are just not optimal for sub-GeV dark matter. The recoil energy from light dark matter scales as dark matter mass squared over the target nucleus. So for sub-GeV dark matter, this is dropping rapidly, and that's where you get this huge suppression below dark matter mass is about 10 GeV. Currently, the best nuclear recoil threshold is around 30 eV. That was shown in the previous plot from CREST 3 with a dark matter reach of about 160 MeV. So the first consideration I'll describe is how we can better understand on the more theory side, how does dark matter actually interact in the material when it's so light? The point I want to make is that dark matter scattering should not be always described as scattering against free nuclei. When the mass is very low, this free nucleus recoil picture does not actually describe the response very accurately. We have a crystal, so we have to account for all the crystal dynamics. So let me illustrate that with this plot showing, as a function of dark matter mass, various energy scales. So this is the total available dark matter kinetic energy, the halo, which just scales as m. And this is if you have a free nuclear recoil, and I've even picked a pretty low mass nucleus here, helium. And so that you see is dropping off as dark matter mass squared. And it's dropping well below the KeV scale, which is where a lot of the experiments are operating. If the energy scales are low enough, the available excitations are actually phonons. So the typical phonon excitation is milli-eV to 100 milli-eV. And that's describing just the lattice vibrations, so the collective excitations of these nuclei in the lattice. So somewhere in between here, you'll have something a little bit more complicated, multiple phonons being produced. So that's one way in which the behavior of dark matter in a material differs from the traditional picture. Another way to look at the material response and detect lower mass dark matter is by using electron recoils. So this red line is showing the energy you could extract from a dark matter electron scattering event. So here the fundamental process is a little bit different because we're talking about dark matter electron coupling versus dark matter nucleus coupling. But if there is a dark matter electron coupling, then you see in this regime, you could extract a bunch more energy out of the electron recoil than out of the nuclear recoil. This red line I've shown is assuming a free electron, which is also not the case. A typical material will have a complicated electronic band structure and eigenstates that you have to consider to actually calculate this dark matter electron scattering. So furthermore, this line, which goes down all the way to milli-eV, is not accurate either. So here's a slightly more accurate picture. It's still a cartoon showing what the actual thresholds are for those electron recoils. So you have, for an insulator, for instance, you might have a threshold of about 10 eV, and semiconductor, a threshold of eV, and for other materials like superconductor or direct material, you might even have very tiny thresholds. So all this is to say that when we look below the GeV scale, we really have to consider the material properties and consider what kinds of excitations are available and the dispersions of those excitations. So far, everything I've talked about is still kind of what I would call a 2-to-2 process, meaning dark matter comes in, it creates one excitation, and then it leaves. But you can also have inelastic processes. And so that will actually be the main subject of my talk. You can have dark matter comes in, it kicks a nucleus, and the nucleus also excites an electron at the same time. So it's a 2-to-3 process. And that will be able to extract even more dark matter kinetic energy out. So again, putting this all together, below the GeV scale, we have a variety of interesting processes to understand on the theory side for how dark matter is interacting in a realistic target. Now let me move on to how that interfaces with the experimental side. And this is a cartoon that's shown often for how direct detection works. When a nucleus gets kicked, the energy in the nuclear recoil could ultimately get deposited into a few different channels, including heat or phonons, lattice vibrations, scintillation photons or light, and charge, by which I mean either an ionized atom or an excited electron hole pair in a semiconductor. And often for the experiments on looking for heavy dark matter, you want to get a couple of these channels, say 2 of these channels, to distinguish your signal from potential backgrounds. So one big challenge is that 2 of these channels start to get lost when the dark matter mass is below a GeV. So in particular, if you have a nuclear recoil below about a few hundred eV, it's not very well understood, but it's expected that the light and charge channels becomes very, very weak. So expected to be 0, or maybe you get a fluctuation once in a while, but not many electrons or photons coming out. And that's challenging, in part because these can be helpful discriminators, and also in part because the thresholds on some of these channels can be quite low. For instance, the threshold on a charge signal could be 1 electron, but the threshold on the heat channel could be somewhat higher, as I said earlier, like a few hundred eV or 50 eV. And so if you only rely on this one, then it is challenging to be able to see these nuclear recoils. Okay, so with those challenges, let me now go into what some of the strategies are that me and many other people are taking to try to look for these nuclear recoils that are from low mass dark matter. One is simply to decrease that heat threshold that I mentioned. You've lost the other channels, but there's a lot of very interesting work that Jody can tell us a lot more about to reduce those heat thresholds to about eV or maybe even below. And on the theory side, what I was describing is that we also want to calculate how dark matter directly excites these phonons, which can be on the scale of 100 millieV. And this is particularly relevant once we're looking at dark matter below the MeV mass scale, as I mentioned. Again, there we can't treat it as a free nucleus, and we really have to directly calculate these processes. So if we can combine these two approaches, then certainly we could access dark matter as light as tens of keV with very small thresholds. That's something that is impressive, but it's also going to be hard. It's not going to happen immediately. So there's kind of complementary approach that a number of people are taking, which is to look for ways to increase the charge signal. So I said that the average expectation for charge being produced in nuclear recoil is very small. But you can rely on a low probability event that gives you a larger charge signal. So you pay a rate penalty, but you get it above the threshold for these charge signals, which can be just like 1 electron or 2 electrons being produced. So one well-known example of that is the atomic Migdal effect. And so this has been applied for liquid xenon detectors. So we model those as just xenon atoms. And when dark matter hits the nucleus, there is where an electron can be excited at the same time. So the idea will be that the wave functions haven't yet caught up to the new moving nucleus. So there's like a small transition probability. And that's already been used to set limits on sub-GeV dark matter with liquid xenon experiments. Another effect is the Bremsstrahlung of transverse photons when this nucleus is kicked as well. So it's kicked instead of the electron being excited, there's a photon being radiated. So those are very interesting techniques, and so far they've only been applied in atomic targets. So what I actually want to talk about today is new work where we study this effect in semiconductors, and we show that you can do even better in semiconductors because the threshold for those charge signals are even smaller. And as I take you through it, you'll see that again, these many body effects, thinking about the details of the material and the crystal target are important to calculating all of these. So to summarize my introduction, I just want to give a big picture of some of the ways in which we can detect nuclear recoils for sub-GeV dark matter. In this MEV to GeV mass range, we can use inelastic processes to look for extra charge being produced. And for sub-MeV, we can rely on phonon excitations and continue to push the development of these really low threshold detectors. So in the remainder of my talk, I'm going to discuss this Migdal effect and plasmon emission in semiconductors. But before that, I think I might just pause for a moment to see if there's any questions, comments.
Yeah, if anybody has a question, go ahead and type speak in the chat window. This is a good place to pause and catch up. Okay, Tom Cohen has a question for you. You should be able to unmute, Tom.
Maybe so I can just.
No. Hi. Is there any assumption that's made on the type of in this scattering? It's always been a mystery to me. There's no assumption made about the type of interaction between the dark matter and the nucleus. I'm still struggling for a picture.
Yeah, that's a good question. I'm assuming an interaction which is the same for both neutrons and protons. Okay. So dark matter just couples to neutrons and protons equally so that all the cross sections kind of scale with the atomic mass squared.
Okay, great, thanks.
Yeah, but part of the, I guess part of the reason that we don't always make those assumptions clear is because I could make a different assumption and it would move the lines around, but it wouldn't necessarily change the qualitative picture. So it's not that important to the final result. That's what I mean to say.
Okay, I don't see any more questions. I think you're good to go, at least for now.
Okay, yeah, feel free to interrupt if there's anything else. Okay, so in the remainder of my talk, I'm going to be describing how we can use this Migdal effect in semiconductors to detect nuclear recoils. So the basic picture that I want to introduce is that dark matter is hitting a nucleus. And I'm going to really treat the nucleus as an ion, meaning the nucleus plus the very tightly bound core electrons. So for instance, in silicon, which is what I'm primarily going to be looking at, binding energy of these is above 100 eV and above. So I just consider them as very tightly bound. Whereas the energies I'm talking about are generally going to be lower than that. So picture is dark matter's hitting now a recoiling ion. And the ion in silicon, it has a charge of 4. And when it recoils, it can emit, it can create basically an electric field, which excites electrons in the material. So that's the interpretation of the Migdal effect that I'll introduce in this talk. It's a little bit different from the standard one, so I will take you through the whole argument for why I think this is a way to think about the Migdal effect. So let me go back and give some context for how I started thinking about this with my collaborators. We were actually motivated by an interesting preprint that appeared early this year from a number of these authors. And these authors were pointing out that there are low energy observed rates in a number of semiconductor direct detection experiments. So here they've plotted those rates as a function of the depth of the location of the experiment. So this one is DOMIC, which is very far underground, and then these are more like surface runs. And what they were pointing out is that there's a number of semiconductor experiments, like here you see blue is silicon, which have somewhat large and similar rates. And there's also germanium, another semiconductor here with red, which is also somewhat similar. Whereas if you have an atomic target, xenon, it's green, it's down here. So what they were suggesting is that maybe these excess rates, these large rates, could be due to dark matter. And more specifically, these rates are observed in the counts for 1 electron or 2 electron events. So meaning you see 2 electron hole pairs at the end. Because they're mainly observed in these semiconductor experiments, these authors suggested that you could be sensitive, you could be seeing a collective effect, which is the plasmon. And I'll describe some more what the plasmon is, but it's a collective oscillation of the electrons, and it's mainly present in crystals, wouldn't be present as much in xenon. And so they suggested dark matter is hitting a nucleus, and during this process, a plasmon is being produced, and the plasmon can decay and it will give rise to these 1 electron or 2 electron events. So this was an interesting excess. What we were interested in is what is this probability to actually produce a plasmon, and how do we understand these plasmons that could be produced from dark matter? So our goal was not necessarily to explain the rates, though if we could, then we would certainly say that, but to just understand the process, because it represents a new interesting process for how dark matter could interact in a semiconductor. And maybe that would give us another way to search for it, which is the point I want to make. Right? So if the plasmon does give rise to extra charge, then it could be an example of that inelastic process. It's an example of the inelastic process, which is low probability, but gives you enough of a charge signal that you can still look for a really low energy event.
So Tongyan, can I ask a silly question?
Please go ahead. Yeah.
So plasmons would be oscillations in a plasma, right? And the quanta of that would be the plasmon. What is the plasma exactly in this situation, since these are cold crystals?
Yeah, I think we can still think of the, if we just ignore the semiconductor for a moment and we just think of a metal, then we have fixed ions and we have the degenerate electron gas. So it's the oscillations in that degenerate electron gas.
Okay. Okay, so it's purely that electron gas that then has these collective oscillations in them that can couple to photons in the same way that phonons can couple to things.
Right. So the plasmon, and I have the next slide is on that, but the plasmon is basically the longitudinal photon in a medium. So yeah, it's a longitudinal oscillation of the, maybe let me just skip directly to this so I can answer that. I'll go back to the previous one. So yeah, this picture is not entirely accurate because I don't have a fixed lattice of ions, but same idea. Like you said, I have plasma oscillations in the electrons. And so that's just coming from displacing electrons by some amount and getting a restoring force. So we get the familiar plasma frequency, which is proportional to the number density. So these electric field, so in addition to the number density of electrons kind of oscillating, you also have the electric field oscillating, and it's a longitudinal electric field. So that's why I'm calling it, that's one reason I'm calling it like a longitudinal photon. It's a longitudinal mode for E fields.
So it's as if the photons have acquired mass. It's a broken symmetry situation effectively in this collective oscillation.
Yeah, exactly. And the dispersion is a little bit different than if it just had acquired mass, but yeah, effectively. So our goal was, the first step of our goal was actually to treat this kind of as a Bremsstrahlung calculation, but to use a longitudinal mode basically being produced rather than the usual transverse photon being produced. And as I said, the kind of assumptions we're making are that we're treating this recoiling ion as, we're still going to treat this as a free particle, which is valid in a certain mass range where the recoil energy is well above the phonon energy, about 100 millieV. But it's not that high, so we don't have to worry about these core electrons. We just treat it as one object, the ion. So this is roughly in the dark matter mass range of 10 MeV to 1 GeV that I'll be working in. Okay, so back to plasmons, which are the quantized version of these oscillations. We started with just a simple toy model for how to think about the plasmon in a semiconductor by just going to a metal. So not worrying about the details of the semiconductor, but just having a degenerate electron gas. In this model, then you can directly compute Bremsstrahlung of this plasmon in an analytic way, which is nice. So let me give a little bit more information about this plasmon. So if I look at Gauss's law without an external source, I've written it here, it has the dielectric function. The important point is that the plasmon is appearing when this dielectric function is going to 0. So when this dielectric function goes to 0, that means you can have a source-free solution with non-zero E field. And it's longitudinal because K dot E is non-zero. So then I have oscillating longitudinal fields. Another way to view it is this is a Coulomb propagator, 1 over K squared. And if I put in screening, then I need to put in the dielectric function. So when the dielectric function goes to 0, then I get a pole in the Coulomb propagator, which means I have a particle, which I'm calling the plasmon. This is what the dispersion of the plasmon looks like in this electron gas model. So this is momentum Q versus energy omega. And the plasmon is here. So it's not exactly the same as if we added a mass term to a photon, because it's actually pretty flat. And it's around 15 to 20 eV in energy. And it's kind of flat in momentum, and it only exists for somewhat low momentum, which is kind of in keeping with the idea of thinking of it as a collective excitation. Up here, the plasmon can decay to electron hole excitations. So all this blue region is available electron hole excitations. So that's why we say the plasmon doesn't really exist up here. But down here where it's sharp, in this toy model, this plasmon is actually infinitely long-lived. Okay, so this plasmon can't be directly produced actually by dark matter. If we take dark matter with a typical halo velocity of about 10 to the minus 3, and you just kind of plug in the kinematics to see what's the available momentum and energy deposition from the dark matter, it's not enough. It's outside of the region where this plasmon exists. But we can produce it by this inelastic 2 to 3 process. So that means dark matter nucleus plus dark matter nucleus and plasmon. And in this electron gas model, it's pretty straightforward to compute this. It's actually just like Bremsstrahlung, except for some small changes. So if you calculate Bremsstrahlung, then normally you would get the elastic scattering rate times some factor in front, which tells you the probability to emit the photon. And it's the same thing here. There's a factor of 2 difference because I don't have 2 polarizations. And the dispersion here, this is the dispersion of the plasmon, of course, is also different for than a photon. So now with this in hand, we can already see things about what this plasmon production looks like. If you plug in the numbers, it will actually be much larger than Bremsstrahlung of transverse photons, because for transverse photons, omega would be approximately K, so it would rise as a function of K, but here it would be just around 20 eV, so you get a much larger value. So that's one thing that's very interesting. To go back to the main point, this is going to be a low probability event. So if you plug in the numbers, this factor in front is going to be 10 to the minus 4 or something like that. But because the plasmon decays into charge signals, it allows even very low energy nuclear recoils to be detected. I think there's a question.
Oh, yes, you're right, there is. So Rob and then Richard. Let me get to Rob here. So I was in the middle of taking notes. Rob, go ahead.
Yeah, so I mean, the Bremsstrahlung channel has kind of had this rate hit compared to the standard nuclear recoil. So coincidentally, it's sort of about 4 or 5 orders of magnitude below the Migdal rate. Does this kind of put it at the same, at a comparable rate for different target nuclei, or is it really atomic dependent?
If I compare this with the transverse rate, let me actually just go to this. So yeah, this is elastic. This is the plasmon, and then this is transverse. So plasmon is actually very similar to Migdal, and as I'll show, plasmon is actually Migdal. Forms a portion of the Migdal rate. So maybe that's consistent with what you're saying, I think.
Sorry, Rob remuted himself here. Yeah, there we go.
Yes, yeah, I think so.
Or,
Okay. Yep.
Okay, and Richard, you had a question as well.
Yeah, the naive question is, what distinguishes this process from neutrino interactions and electrons?
So good question. Are you asking like, would neutrinos also give the same effect?
Well, we know that neutrino colliding with electron will transfer most of its energy to the electron. That's been calculations by Dicus and somebody years ago. And you're entering the energy range, which is consistent with solar neutrinos. That's what I'm trying to understand. What is the difference here on the observations?
Yeah, so one thing is that what I'm looking at, I'm assuming the dark matter dominantly couples to neutrons and protons so that it's not directly scattering off the electrons. You're right, if dark matter can directly scatter off the electrons, then in a particular model, that might be a larger rate than what I'm looking at. But in some models, the dark matter has a small coupling to electrons, and it wouldn't produce much dark matter electron scattering. And the other thing is that you're definitely right that neutrinos would also give the same effect. So you could redo kind of everything here for neutrinos instead.
Okay, thank you.
Okay, I don't think we have any more questions at this stage. Oh, wait, I take that back. Tom has a question. Go ahead, Tom.
Yeah, I was just, when you mentioned plasmons, you had, you had this expression for a simple harmonic oscillator, and it just got me thinking that the plasmons presumably have quantized energy levels. I mean, there's no resonance effect that might enhance the detection probability in the sense that I don't know, you excite one of these excitations, higher order excitations of the simple harmonic oscillator, and maybe this liberates more than the 1 or 2 electrons.
Yeah, so I think you're saying like we're looking at exciting one plasmon, and I think the picture you have is right. It's like you're resonantly exciting the electrons in a way that you get the plasmon, but you could have like 2 plasmon. Is that what you're saying? Like,
Yeah. Well, for example, yeah.
Yeah, you could also have the 2 plasmon. Yeah.
And then I was thinking you could then maybe, I don't know, this is by a judicious choice of the crystal, you might increase the likelihood that the interaction couples to the n = 2 level, say. Oh,
interesting. I haven't thought much about the 2 plasmon, right? I think in terms of like silicon, the 2 plasmon part is weaker. Like if you take this, I'll show you a version of this plot, which is for more realistic, and you look like up here twice omega p, it is a weaker resonance, but I haven't looked much into that.
I'm teaching quantum, so I have simple harmonic oscillator on the brain.
Yeah, well, a lot of my talk is just quantum and electromagnetism, so.
Okay, I don't see any more questions for now.
Okay. Okay, so I was here and I was just describing what the rates look like in this toy model. So we get a much larger rate for this plasmon emission compared to Bremsstrahlung of transverse modes. And this is nice. We can use it to increase our sensitivity. But whoa, you might say this is just a toy model. What about an actual material? So for the rest of my talk, I'm going to start to introduce the things I need to deal with an actual semiconductor. So if you remember that plot I just showed with the plasmon and the electron hole pair in the toy model, this is a numerical calculation of what the response looks like in an actual semiconductor. So everything gets washed out a lot, of course. You still see the plasmon resonance here. It's this thing, this dark blue region. It's a lot wider. You see it's actually pretty wide. And then this is all electron hole excitations. So some of the differences for a semiconductor, one include the fact that you have to account for a band gap. Of course, you have to account for all the electron wave functions and also account for this width of the plasmon that's appearing. So we can't deal with that in the toy model. Instead, the way we dealt with this was to rewrite the rate, the plasmon emission rate, in terms of just this dielectric function. In that way, we can use numerical calculations of the dielectric function that are, well, numerical calculations that are first principles for particular materials. Okay, so let me give you the one slide derivation of that. It's just electromagnetism. So I treat the ion now as a current source. So it has V ion and it turns on at some time t when dark matter hits the ion. The energy transfer to the material will be this J dot E. And then I solve for the E fields using Maxwell's equations. So I use the longitudinal part of Maxwell's equations specifically. And here you see that the source, which is this current, will source this E field with a dielectric function in front. And so for Maxwell's equations, I plug it back in the E field in here and here, sorry, and you'll see I get energy transfer rate, which is just in terms of a currents and 1 over this dielectric function. So that's what it looks like. And this is the energy loss rate. And you see this imaginary part of -1 over epsilon. For any of you who do like charge energy loss of charged particles and materials, this might look familiar. It's called the energy loss function, which so it's commonly studied material or object. So the picture is now we create this current, and this current will lose energy through this loss function. And you see also this -1 over the dielectric function. Well, when the dielectric function goes to 0, that's when I have the plasmon. So you see there can be a resonance in this function. That's the plasmon. And this is a plot showing what that function actually looks like, the energy loss function. So here, this is at 0 momentum, and the solid line is from an X-ray scattering experiment. And this resonance is exactly the plasmon. So if you send in like an electron, then it can lose energy to this one plasmon at 0 momentum. The dotted line is actually the toy model we started with, where we just modified it a little bit to include the width, this finite width of the plasmon. And so here you see the energy loss function at different momentum transfers. And that actually the toy model is pretty decent at reproducing the broad features of this. Okay, so with that in hand, what we found was that mostly validated this toy model where we calculated plasmon production. And we found, as was noted earlier, rates that were about 10 to the minus 4, 10 to the minus 5 of the actual nuclear recoil. And so we pointed out in that first paper how you could use this to set much better constraints or do stronger searches for dark matter nucleus scattering. But there's something else interesting here, which will lead to the final part of my talk, which is that this energy loss function, it does contain a plasmon resonance, as you saw in the plot. But it also contains lots of other things. So it contains all electronic excitations. You can look off the resonance. There's no reason to look on that you have to look at the plasmon. And as I mentioned earlier, you can use numerical calculations to try to see how big all of those contributions are and get this full rate for plasma for this inelastic process, which I will stop calling plasmon production shortly, because as I'll show, we actually get a lot more rate off of the pole. Okay, so I'll pause again if there's any questions, but in this last part, I'll explore now all our gory calculations of this quantity and what the actual numerical rates look like.
Okay, yeah, any questions before she gets to that last part? All right, I don't see anything, so I think you're safe to proceed.
Okay, thanks. Just like to pause.
No, that's very healthy. You're a good model for students that are doing their teaching practicum this semester.
Okay, good. All right, so I paused because I was about to show this large equation on the next slide. So in our newest work, which appeared last week, we looked at this in more detail in semiconductors. We did a couple of things beyond just numerically calculate the dielectric function. So let me explain this diagram a little bit. So when we scatter off a nucleus inside a lattice, we can think of the nucleus as sitting in this harmonic potential. And the frequency associated with this harmonic potential is actually omega phonon, about 100 millieV. So in the process, we're computing dark matter scatters, and we immediately emit this Migdal electron, as I'll explain shortly. And then eventually the nucleus might go off and lose energy as it goes to this part of the potential and emit phonons. So because the nucleus, the ions are not actually free in a target material, one of the other things we did to firm up our result was to look at this, to treat this more quantitatively. So in particular, we wanted to treat the fact that the initial nucleus is actually in this harmonic potential, in this harmonic crystal, as opposed to being free. So if we combine everything, I'll just show you the rough ingredients of this final cross-section. So this is a cross-section for the inelastic process. And as before, we'll factor out the usual dark matter nucleus scattering. So everything else is the probability. We account for this harmonic potential with a form factor. So this is what I just alluded to. And then everything else here is actually just the energy loss function, written in a slightly more complicated way, but just the energy loss function. And there's more indices now because I'm actually accounting for the periodicity of the lattice. But otherwise, it's pretty similar to before, just slightly uglier notation. And here are some plots showing the numerical calculations of the energy loss function now. That's this red line, GPaw, as again compared to various measurements with X-rays or optical data. And that's the blue. Note that if we had measurements along every direction and every momentum, then you could also just use the measurement directly, but not all the data is not, available for every single momentum in every single direction. So we just used one of these ab initio codes to calculate the energy loss function. Okay, so we calculated this and it's all interesting, but there's another interesting layer to this, which is that it's actually related to the atomic Migdal effect. So to explain that, let me go back and review what the atomic Migdal effect is. So dark matter in this picture is coming in, hitting this nucleus. Here's the electron in its bound state. And the picture is when the nucleus moves suddenly, the electron wave functions are still in their original state, as indicated by this cartoon. And that has some overlap with the excited states about the moving nucleus in this last picture. So the way that's calculated is then by saying the initial state, we boost to the frame of the moving nucleus. So that's the wave function in the second part. And then we just take the overlap with the final possible states for the third one, and we square that to get our transition probability. So that's kind of the standard way to explain the atomic Migdal effect attributed to Migdal. The issue with this explanation is that it's not very obvious how it generalizes to semiconductors. The problem is you have a whole lattice of nuclei. So if you boost your electron wave functions, it's really as if you were recoiling all your nuclei, which is not really what we want. Okay, so there's a preferred frame of reference in a crystal, and you can't just boost so easily. It's not so obvious that you can use the boosting thing. So the claim that we're making is that the rate that we derived is actually a generalization of the atomic Migdal effect to semiconductors, which doesn't rely on this boosting argument. And furthermore, we think there's another simple way to understand the effect without relying on the boost. And you can see it again through just through quantum mechanics. Like I said earlier, a lot of my talk is quantum mechanics and electromagnetism. So the matrix element for the atomic Migdal effect was given by this dipole moment R, which came in, apologies, it came in because dark matter, because for dark matter nucleus scattering, this velocity is very small, so you can just take the first term. So I can rewrite this matrix element for the atomic Migdal effect. For a dipole, I can rewrite it using the momentum operator. And then again, I can rewrite that in terms of the commutator of momentum and the Hamiltonian, because these are energy eigenstates. And then finally, this commutator will just give what the force on the electrons is. And the force on the electrons is coming from the nucleus, right? So it's just dV dr. And so finally, what we see is that this matrix element can be rewritten in terms of the potential from the recoiling nucleus. And this is actually the dipole potential. So you see here Vn dotted into R. So that's like our usual P dot R potential for a dipole. And this is just the Fourier transform in time, accounting for the fact that we're looking at energy eigenstates. So that gives an interesting physical interpretation already, that we're just looking at the potential from a recoiling nucleus, which can excite an electron. I'm going to take one more Fourier transform to turn it into a form that looks a lot like the semiconductor effect that we derived. So if I do the spatial Fourier transform, then I get this emission probability this probability to excite an electron. And you can see that actually it does have a very similar form to the semiconductor Migdal effect. Right, so they both have overall scaling with some charge times alpha over omega to the fourth. And they both have some matrix element with this e to the I kr. And this Vn also appears. So essentially they have very identical forms, and there are some small differences because, of course, the systems are still different. And this last piece is what we derived, basically. So the interpretation we take from this is that we can think of the Migdal effect as some analog of Bremsstrahlung that's happening in a medium where you have all these electrons around. When you kick a nucleus, it will generate potential, a time-dependent potential, and that can excite an electron. So that's a fairly, I think, simple thing that we expect to happen. But I think what we're trying to say is that in the atomic Migdal effect, we can also use this as an explanation. We don't necessarily have to rely on this boosting argument. And as I just showed, the form of the rate can then be cast in a very similar way in both cases. So you might wonder at this point, like, if the first thing here is equivalent to the last thing here, and you just rewrote it, like, what was wrong with just starting from this first matrix element in the first place and using it in semiconductors? The problem is that if you go through this operator logic, at the end in a lattice, you would get the contribution of the dipole potential from all of the nuclei in the potential. Right? If you take this commutator, you'll get a sum over all ions in the lattice. And so this operator relation does not actually hold in semiconductors. If you start from the left side versus the right side, you'll get different answers. And particularly starting from this side, you would generate the dipole potentials of all nuclei, which is kind of consistent with what we were saying at the beginning, that if you apply a boosting argument, you're really boosting all the nuclei as opposed to just one. Okay, so what we're arguing for is starting from thinking about this in a dipole potential way and starting from this latter form of the matrix element. All right, so I've shown now the connection to the atomic Migdal effect and why I think this should be called the Migdal effect in semiconductors. Let me show you finally some results in the last few minutes. These are the rates in silicon. So on the left, there's a couple different lines. This blue line is where we cut the rate off at small momentum transfer, and this bump is actually the Plasmon resonance. But you see, when we included everything in our numerical calculations, we get the green line, which is a much larger rate. The scaling of this rate goes as 1 over energy to the 1 over omega to the fourth. So when you have a lower threshold material, you tend to get larger rates. And so you can see that, for instance, in comparing with the dotted orange line. The dotted orange line is if you took an atomic silicon target, which has a higher threshold, that's the rate you would get. So we think looking for this Migdal effect in semiconductors is particularly powerful because of this lower gap. And for the experts in the audience, you can also turn this rate into the actual number of detected electrons. So it's a histogram of 1, 2 electron hole pairs, et cetera. And that's what the rate would look like. Okay, so then finally, this is my last summary slide, or last summary slide of this topic. Putting that all together, we show these curves, which are projected sensitivity to dark matter nucleus scattering. And this is with this Migdal effect in silicon and germanium. These are the projected sensitivity if we have a kilogram year exposure and put a threshold of 2 electron hole pairs. These numbers are very similar to some exciting lots of exciting experimental proposals and developments. So maybe Jody can comment more, but I'll just say these seem like in target for a lot of different experiments. But the current, like if we try to take current experimental results, here is one, for example. This is from a surface run from Sensei with fairly small exposure, then you would get this red limit up here. You can also compare with what a xenon target would do. So this is liquid xenon, 100 kilogram year, so a lot larger exposure, and same 2 electron threshold. You can see because the threshold is going to be higher in these atomic targets, this sensitivity is actually a little bit weaker despite the larger exposure. Okay, and the last thing I'll just comment is that these bands are showing our theoretical uncertainty due to the fact that we're not accounting for the phonons in detail here. So we're well, let me restate that. That wasn't quite accurate. When the dark matter mass is very low, we produce single phonons. And when the dark matter mass is very high, we take a single nucleus. And in between, something a little bit more complicated happens and requires more work to treat that properly. So dark matter is exciting a bunch of phonons at once. And so the fact that these bands are kind of growing is showing that that's the mass range where we have to treat it with a different approach to account for the multi-phonon processes. Okay, so just to wrap up, we introduced this Migdal effect in semiconductors, and we showed how you can use it to improve the sensitivity now by using rare charge signals for sub-GeV dark matter. And in my last slide, I'll just connect it back to the bigger picture of looking for dark matter below the GeV scale through a range of different approaches, all the way down to dark matter mass of keV or so. And with that, I'll conclude. Thank you so much for listening.
Okay, no, thank you very much. And we try to give you a little applause here at the end.
Oh, great.
It's something, right?
Yeah.
So we have a question from Tim Hobbs. Tim, let me get you unmuted here. Go for it, Tim.
Can you hear me?
Yeah.
Okay, great. Yeah, thanks. This was a really interesting talk. I have a question which you may have alluded to, I think, during the course of your prepared comments, which is similar to what I always ask in these kinds of direct detection discussions. So you presumably have some theoretical uncertainty just from the nuclear wave function or the nuclear recoil, that aspect of the dark matter nuclear cross-section that you've been talking about. You had mentioned at some point ab initio calculations. I'm wondering, is that a contribution to the exclusion plots that you showed toward the end? Or how well is that under control at this level, would you say?
So let me see if I'm understanding correctly. So for the dark matter and nucleus scattering side, for very heavy dark matter, there can be uncertainty because of the because of the nuclear wave functions and how basically there's like a form factor for how the dark matter interacts with the nucleus. Is that roughly the uncertainty you're talking about? Or is it a different one? Because here I'm talking about, because I'm looking at sub-GeV dark matter, the nuclear wave functions don't present a large uncertainty because the dark matter nucleus scattering, it's so low in momentum transfer that we can coherently sum over all the nucleons without any like nuclear uncertainty about the form factor. But I'm not entirely sure if that was the, okay.
Yeah, thank you. I couldn't unmute while you were asking. That is the gist of what I was getting at. I mean, my assumption was more or less what you were saying, that it's so low energy that indeed you make this assumption. But yeah, that sounds reasonable. So in general,
Okay, yeah.
there's no input, in other words, really directly from nuclear modeling or anything of that sort then directly in this calculation.
That's right. Yeah.
Right.
We do have like the theoretical uncertainty you mentioned. You were alluding to the ab initio calculations.
Right.
So yeah, indeed, for the energy loss function, we're using numerical calculations that agree reasonably well, but there might still be, order one uncertainties there.
Right.
So,
and what is that exactly? I mean, can you say a word about, I mean, what are these calculations exactly?
These are the density functional theory codes.
I see.
Yeah, there are a lot of those, and we used one of those that can calculate this dielectric function.
Very good. Okay. All right. Thank you.
Sorry, there's actually a discussion going on the YouTube channel, which I think has never happened before. So thanks to everybody who's talking about phonons over on YouTube. While we're waiting to see if anyone else has any more questions, I had one for you, Tongyan. The Migdal effect, help me out here. Has that ever actually been detected? I mean, it seems like a pretty inevitable consequence of quantum mechanics applied to these systems, but has it ever actually been observed?
There are a lot of, there's a bunch of literature from, I want to say, I'm not going to get the decade right. So there's a bunch of literature looking at, if you take a neutron and you hit a nucleus, you should see the same effect. And if you take another effect is if a nucleus decays into an alpha and it emits an alpha, it also will recoil. And you should see an effect. So I think it has been observed in like nuclear decays, and I think also the nucleon nucleus scattering. But in all those cases, it's also complicated by other interactions. Like in dark matter, we kind of have the, we can say, okay, dark matter only talks to the nucleus in one particular way. That simplifies things. Right. We don't have to worry about the alpha also has the electromagnetic interaction. Or if in the nucleon case, you can also get some like resonant strong interaction kind of effects. So yeah, it's been observed. I'm not sure the data is extremely clean on the interpretation because of all these effects that you have to include.
Mm-hmm. So, I mean, since in a sense you've maybe generalized isn't the right word, but broadened this effect into the context of whole semiconductors, what are your thoughts on it? Like if somebody said, okay, we're going to give you X millions of dollars to construct an experiment to actually try to observe this effect in a controlled set of conditions, it seems like, well, maybe you'd want to put this near some low energy neutrino source or something like that, or maybe a very low energy neutron source, although presumably you'll be competing against the capture cross section as well there. So what would you do? What would you do if you wanted to build an experimental team to go and actually observe this effect and get data on it before you apply it to a dark matter experiment?
Good question. As a theorist, I don't know if I'm going to give the best answer, but I think if you could do it with neutrinos, that would be great. Like put it next to a reactor.
The trick is ideally you'd want to know beam on, beam off. And so having a beam that can do spills where you've got pulses of neutrinos coming through in a certain direction is ideal, but maybe not necessary for this. Maybe you just need to cool the detector down somewhere in the vicinity of a low energy neutrino source and just watch.
Yeah, the thing is, well, I can't comment on, which source do you want to use, neutrinos or neutrons? From the perspective of like teasing out this effect, I get the sense neutrinos would be a little bit better because it did sound like for neutrons, there can be some resonant effects.
Right.
So that, from what I saw,
you could go to like the spallation neutron source and try to do this that complicates things through the strong interaction, presumably. So, okay, I was curious because, I mean, Richard brought up earlier this question of neutrinos. And I mean, obviously, if neutrinos can strike the nucleus, which they certainly can, they could also induce this effect. So it should be detectable if you flood a semiconductor with neutrinos and just wait, right?
Yeah, on the other hand, neutrinos can also kick out electrons in other ways. So
right, but they won't double scatter.
That's tough.
Like the probability the neutrino hits a nucleus and then hits an atomic electron is vanishingly small, right? Whereas the alpha particles you mentioned earlier will create havoc because of the electromagnetic interactions they'll then also generate. So
yeah, I guess another thing is like, even if the neutrino is scattering off the electrons, I think the spectrum would be really different from this effect. So that might help.
right, and presumably there well, maybe if it's low energy enough, it wouldn't actually eject the electron, but presumably it would lead to some other signals that would be distinct from the nucleus getting struck. But
well, that's a good question, though. That's a very good question.
Yeah, I mean, I've heard this discussed obviously in the context of dark matter experiments before, but the experimentalist in me hungers to actually measure the effect itself, independent of, say, dark matter. So
yeah, absolutely.
All right, any other questions? I don't see any more right now in the speaker chat, but we did have a lot of things during the talk. So clearly your subject was interesting, or you wouldn't have gotten so many questions during your talk. All right, I don't see any more questions. So I think let's go ahead and thank Tongyan for her kind offer to do this presentation today and for all the information she's provided. And I'll just wish you all a good night and a safe Thanksgiving. I hope everyone has a safe and easy Thanksgiving, okay? All right.
Yeah, thanks again.
Yeah, no, thank you. Bye-bye. Bye, everybody.
Thank you.